Okay, let's start it. So we will talk about hybrid systems. Okay, a hybrid system is a system where the dynamics needs to be described by different equations of motion for different times. Um, Unknowing to you, you've already done this before when you program the Pong game. The Pong is actually an example of a hybrid system. So a ball bouncing on walls is a hybrid system because you need one set of equations to describe its movement in the air and another set to describe how the collision will take place. I think we use the coefficient of restitution 1 in that case. Um, so examples of so let me just put the definition here. Hybrid system is the one which has dynamics change with time. Examples would be the Pong game. A real life example would be a ball bouncing. Uh, we also see this in day-to-day life, which is when you walk, you are actually a hybrid system because there's a phase when one leg is on the ground and the other leg is swinging, and there's a phase when both legs are on the ground, and there's a phase when both legs are going to apply forces. When you run, both legs leave the ground. So because you switch between flight, a phase when both legs are in there, one leg is on the ground, two legs are on the ground, your walking, running is actually a hybrid system. So walking, running, hopping are all hybrid systems. Okay, so what we'll do here is I will introduce the simplest hybrid system, a bouncing ball. Eventually, we'll get to a hopper, a one leg or a pogo stick, and we'll keep it there. But you could model a person walking also with the same kind of ideas. So here's the example we'll do first is a bouncing ball. Okay, so what we'll do is we'll do a one-dimensional bounce. So if you have a ball, let's say this ball, and then you drop it from a height or drop it up or down, doesn't matter how, the ball will move down. It will be here at some instant, right? It's going with a velocity v downwards. But then after the bounce, it'll come up with a velocity v2, and then it'll keep bouncing off. So the question is, how do we, so how to simulate, animate, analyze such systems? So far we've not seen that, and we'll see this now. So what we need to do in this case is to take a closer look at how the system behaves, identify the different phases of its movement. For each phase, we need to write equations, because once we have the equations, we can put it in Python and then integrate the equations. And then once we have the data for the system as a function of time, we can do animations and see if it behaves the way it would behave in real life. So for a bouncing ball, what we can think about is I would say, there are three things we need to keep in mind. The first is there is a phase where the ball is in the air. It's basically a free fall. So let's take the ball. And drop it. So this is free fall. Free fall. It falls under gravity. Okay, so it doesn't stay in the air for long, right? In no time, it will be touching the ground. Okay, so when it's about to hit the ground, its velocity would be in the downward direction. And then once it uh, reacts against the ground, the same ball would have a velocity in the upward direction. I would like to call this as V negative, just to indicate the velocity before the bounce, and then V positive to indicate after the bounce. So this is free fall, and this is the bounce. Okay, so I guess we know how to write the equations for free fall. It's just falling under gravity. To describe the movement when it is taking off from the ground, there's something called coefficient of restitution, which I'll talk in just a bit. You also had, well, we did not use the coefficient of restitution in the Pong game, but it was in there when we said the velocity after the collision is equal and opposite to the velocity before collision, that we assume that the coefficient of restitution was 1. But we'll get to that. But there's some management you need to do in order to simulate this. So what we'll do is, let's say that the ball, we started in free fall. Okay. Now, you start at time t equals 0, the ball is falling down. You don't know ahead of time when it will hit the floor. If it's dropped from 1 meter versus 2 meters, it's probably going to take more time to fall from 2 meters than 1 meter. So we do not know ahead of time how much time will it take to hit the ground. So we need to first be able to detect when it hits the ground, right? So the detection is by itself a challenging thing. It turns out there are tools in MATLAB to do it, or sorry, Python to do it. There is the ODE integrator actually can stop integration when certain conditions are missed. So we will detect ground, and let's say that we assume that the ground is at y equals 0, but it can be y equals h. Okay, y is equal to 0, y equals h. So once we detect ground, we need to use the equations for bounce, right? What happens to the ball after it collides with the ground? In this case, clearly the velocity is going to be pointing upwards after the bounce. Once it takes off with a velocity v positive, it'll again go in free fall, and the same equations can be written as we wrote earlier. So free fall, and then it'll keep going bounce. So free fall, bounce, free fall, bounce. Okay, so what we notice here is that we see a pattern. We see that there is, by the way, detect ground should be here. So we see a pattern. We basically have free fall bounce happening numerous times. So what we need to do is we need to identify this repeating unit. So let's say that if we start here, and if we can describe the movement of one bounce, one complete bounce, that is start from flight phase, hit the ground, come back up, then we have basically, we can just take that unit and just keep repeating it any number of times. This is the repeating unit. Okay, so what we'll do is we'll basically write the equations of these two phases. There's free fall. We need to detect ground, and then the bounce. So let's write the equations for that. Some of them are transitions, like the ground y equals 0 is a transition condition. It's not really equations of motion. There's no physics in there. It's just what they call kinematics, right? When the ball height is, in this case, if the radius of the ball is r, when y equals r, it will hit the ground. If you think the ball is has no radius, it's zero radius, then y equals zero is the height. Okay, so let's take this and start describing the various parts, one, two, and three. Um, so here we go. First is free fall. So we have the ball under gravity, and then we like to keep y as upwards. In fact, you can move it down here. Now I could write this equations using Euler-Lagrange, but just an overkill, right? We just know the equations. It's basically the acceleration in the y direction is minus g, and then we really don't need to consider movement in the x direction. I'm not launching the projectile in the horizontal direction. It's just going to be vertical movement. You could extend this to two-dimensional movement. So this is just what we need for describing the free fall. Super easy, just this one equation. The second one is when we have the contact, that is when the ball hits the ground, we need to stop the integration. So we need to find the time when y equals 0. This is y equals 0. So we stop the integration. In fact, you did that too. When you did this whole thing about the pong ball, you basically find when the ball hits the wall, and then you need to switch something. You need to change something in the velocity, right? So that's the third part, that is the bounce. So if we have the ball coming in with a velocity of v minus, or if you like, in the language of the degree of freedom, which is y, you would call that y dot negative because it's velocity, and then y dot positive. Velocity before bounce. Velocity after bounce. Okay, now it turns out that there is no fundamental principles behind modeling a bounce. What I mean by the fundamental principle is that when you wrote F equals ma, that's a law which is followed by any object, at least on Earth, moving at reasonable speeds. Okay, it's a fundamental law of motion. But for the bounce, there are many ways of modeling it. One way, which is sort of, these are known as empirical laws or phenomenological models. They're based on experience. Okay, what Newton found is that if you can use this, you can use a single number to describe this particular phenomenon. It's called the law of restitution. Okay, it is not a universal law. You could potentially find a surface which doesn't follow this law. It's just that most surfaces will follow this law. It's basically saying that the coefficient of restitution, E, is the velocity p4 after impact divided by the velocity p4 impact with the negative sign. So E is the coefficient of restitution. Okay, the negative sign here is so that when you start with a velocity y dot negative in the downward direction, the E ensures that the negative direction basically ensures that it goes in the opposite direction. Now, this E is found just based on no, there's no there's no there's no physics involved here. It's just matter of experience, right? You bounce, you take a ball of certain material, you bounced on, let's say, carpet, it will show a certain behavior. You take the same ball, you bounce it outdoors on concrete, it will show a different behavior. It depends on the material itself. So when E is equal to 0, we call it plastic collision. When E equals 1, we call it elastic collision, right? When plastic collision means that if you put E equals 0, you see that the velocity after the bounce is 0. If you put E equals 1, you'll see that the velocity after the collision is exactly the same as the velocity before collision, but change in sign. So it's going to just spring up the same height after it bounced. And in the real world, what you'll see is E is between 0 and 1. Can E be greater than 1? No. Okay. We'll come to that a little bit later. Unless it's on trampoline, yeah. Unless there's a, well, I guess the rationale is unless you power it somehow, the trampoline has to, something has to provide it energy to uh, make it greater than 1, in which case the way it works is if you drop a ball from a height h, then after a bounce, it'll come back to h, which means that E is 1. If height is 0, it means that if it's a plastic collision, and your experience shows that if you drop it from a height h, then the next bounce is going to be less than h. If it has to be greater than h, then you need to inject energy into the system. But we'll get back to that a little bit later. Okay, so let's see how to simulate this in Python. Okay, we have the equations. That's all we need. So the simulation proceeds as follows. So what we'll do is we need to write, so we need to do some bookkeeping. So we're going to write a function called one bounce. Okay, so the one bounce would have the following things. It'll have free fall, detect, ground, and then bounce. Because what we said is we can take this and just repeat it any number of times to make it look like it's bouncing multiple times. So for free fall, we just need to go with y dot double dot equals minus g. To detect contact or detect ground, we do stop. So by the way, when I say free fall, you need to take these equations and integrate them with ODE int. So here you need to stop integration when y equals 0, and you could change that y equals to h or whatever you want. It's not a problem. Okay, so there is a function called solve IVP. This is for integration. It's called solve IVP. With IVP here means initial value problem. You need to give it the equations. So y double dot equals minus g. Okay, and then you typically want to break it down as y double dot equals minus g. It will actually be broken down into two first-order equations. So one will be, so you need to break it down into let's call it vy is minus dot is minus g, and then y dot is vy, right? These are they are broken down into two first order equations. So this function, if you give the EOM, if you give it the time, so let's say T0 TF. Now here's the thing, I know the initial time, but I don't know the final time because I don't know till what time, when will the bounce occur. So what you can do is you can specify, after this is specifications of the initial conditions, initial condition. Like maybe you bounce it off from a height of 5 meters and then you give it a velocity of, I don't know, 5 meters per second. Okay, next argument to this is any parameters. Sorry, it's a method. Let's go down here. Okay, in Python, the way you write a new line, if you don't want to keep continuing, you just put a backslash. That means you can continue on the new line. So then you give the method. Okay, I said RK45, Rungekutta 45 is a very popular method. So we'll use that. Okay, now you need to also pass one more thing. There is something called an event, and this is very important. It's called an event. Okay, the event is you need to tell it that when should you stop, because this cannot go forever, because if the integration goes forever, the ball is going to inside the ground. You need to stop when the ball hits the ground. So the event, and we'll give it a function name. Let's call that event contact. This basically supplies it the fact that y equals 0 is when you should stop. This is the event we're looking for. When y equals 0, we want the integration to stop. Okay, and then there are other things you can give parameters and so on, but the main thing I want to highlight is that you need to pass it here, right here in the IVP function, the integrator. Okay, and then finally, once you find the time it falls, you then have to use the bounce equation. Whatever is the velocity before impact, you need to multiply it with minus e times y dot and get y dot positive. And then once you set it up for y dot positive, then it again goes to free fall, and you just keep repeating this. So I'm going to show you code which does this, which basically simulates a bouncing ball. And this is kind of interesting because once it does it and once we animate, we can try to get a feel of it, try to see if it looks realistic. And I think we ourselves, because we know how a ball bounces, we can actually maybe relate to it, right? Identify if it really is physics-based simulation or not physics-based simulation. So when you look at, for example, cartoons, when they don't use physics-based simulations, you'll see that the ball, when something is flying in the air, it will behave weirdly because they don't use a physics engine to do it. They just use an animator who is trying to sort of guess its way through. And sometimes, there's exaggeration in cartoons, but way to fix it is to use physics-based simulation, which is by itself a field. Okay, so let's see how to do this. Okay, so this is a bouncing ball. It's pretty long, but a big part of this code is actually just setting up things. Give it some time. Okay, so that's the simulation. Now I'll show you the parts, but here what I put was a coefficient of restitution of 0.9, and that's how it behaves. And I think you can get a feeling if it looks right or not. It's probably not very accurate. So the times I refresh it, depending on the speed of my computer, you might have to change with the pause so that it looks realistic. So if you play this on my Mac, it plays at a different speed, plays over here, plays at a different speed. But let's look at the code very briefly. As I said, there's one bounce, which is the main building block. And I need to sort of guess when the collision will take place. So I really, if you think the collision is going to take 1 second, I integrate for 5 more seconds because the collision will take between this time. Then I call projectile with, you can see this, the time, the right-hand side, the method, the event contact, that will basically say if it's bouncing or not. So contact is basically this function. All it's returning is y. So it needs to find the time when y equals, in this case, 0. If you want to do y equals -2 or minus 0.5, that'll work too. So just one change, and you can simulate it bouncing over something which is 0.5 meters high. So you'll see it happen here. There. It's an invisible horizontal plate, but I could put anything there, but it works. So okay. Okay, so that's okay. So then that's contact. So this is the piece over here. And let's see. So bounce, and then here is where I actually use the coefficient of restitution. So there's a parameter called E, and that E basically switches the velocity from downwards to upwards, and I return that. And then the main, so there's a piece which animates, and you guys are now pretty good at that. There's a projectile piece, which is basically just sending the equations of motion. In this case, assume the drag is 0, though I put drag, the drag is 0. And let's see, so initialize the position velocity. And then I run a loop for whatever 10 seconds. And then each time there's a bounce, it basically just it keeps track of each bounce, puts it all together. And once it puts it all together, it can animate the whole system using animate. So that's how it is. Now, I said one important thing here is that there's a coefficient of restitution. You could change that 1.1, and then it will do something which you don't expect it to do, right? In real world, it shouldn't be bouncing higher than what it started from, but with a coefficient of restitution greater than 1, it will bounce higher.